Hello, and welcome to Sets and Set Operations. My name is Tuesday J. Johnson. I'm a lecturer at the University of Texas, El Paso, and an assistant professor at Doña Ana Community College. So, let's start with some definitions. A set is a collection of items. These items are referred to as the elements of the set. So you could have a set of primary colors, red, yellow, and blue. Maybe you have a set of all the towels in your linen closet. Maybe you have a set of the first 10 integers. It's first 10 positive integers. It doesn't matter. It's just a collection of items. We'll use little squiggly brackets to enclose a set. They don't have to be good. We usually use capital letters to represent a set, and then we'll use lowercase letters for elements that are inside of that set. Alright, so the set A has element little a. So, what does it mean to be an element? Well, first of all, this is the crazy looking E. This symbol means element. So little a is an element of set A. Means that little a is an element of the set A. That's what the E means. It means it's a member. If B is not an element of the set A, we would put a line through the little element symbol saying B is not an element of set A. Two sets, B and A, are equal, means that A and B have the same elements. The order in which the elements are listed does not matter. So if we look at the US flag, red, white, and blue, and we look at the French flag, blue, white, and red, same three colors, order does not matter at all. So those two sets, set of colors in the French flag and the set of colors in the US flag, would be equal. B, and then the symbol that looks a little bit like a less than or equal to, but it's roundy. It looks like a C, all right? Less than or equal to. This is contained in. So B is contained in or equal to A, means that B is a subset of A. So every element of B is also in A. If you take the colors A to be all the colors on the Olympic flag, and set B, the colors of the US flag, all colors of the US flag show up on the Olympic flag, but the Olympic flag has more. This means that the set of colors of the US flag is a proper subset. Proper subset, if there's no equality, of the set of colors on the Olympic flag. So B is a subset of A, but they're not equal. We have this special notation in math. It's an empty set. The zero with the line through it. I know a lot of people use that just for zero in computer programming, but in math it has a specific meaning. It's the empty set. It's a set that contains no elements. For any set you have, set colors from the US flag, a subset is nothing, right? I don't take any of those colors. So the empty set is a subset of every set. Now I hope these are obvious facts. These are kind of those duh math moments. We call a set finite if it has finitely many elements. All right, a finite set might be the set of students in one particular class. An infinite set does not have finitely many elements. Maybe, hopefully. So the set of natural numbers never ends. You can't count them all, and therefore it's infinite. There's no stopping point, there's no finite stop to it, so it's an infinite set. So, some standard sets and what they contain. A standard coin has two outcomes when flipped and noting the side face up, and the set of outcomes is either heads or tails. If you ever have a coin land on its side, just standing up on its edge and it's not in a groove or anything, that's cool. Take a picture of it, send it to me. Put it in the comments. I'd love to see it. If two coins are tossed, there are two possibilities. Suppose we use 2 quarters. Right? We don't know whose quarter is whose. Either we'll have 2 heads, 1 head, or no heads. And those are the only 3 options. But if we flip maybe a quarter and a nickel, or a quarter and a penny, then we could have heads, 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 tails, tails, heads, and tails, tails. Notice that when the coins are distinguishable, we have these 2 different representations where there's only 1 head. When the coins are the same, indistinguishable, it's just 1 outcome. But if I have heads on the quarter and tails on the penny, that's different than tails on the quarter and heads on the penny. So we have to list them differently. For more sets involving dice, coins, and playing cards, I have a handout cleverly entitled Dice Coin Card, and you can find that on my website, www, why would you put that? Anyway, math.utep faculty. Oh my goodness, faculty slash. Oh, that's not gonna help. Can I move that? Oh, look at that. Slash Tuesday J. Tuesday J. Horribly written, but that's my website, and look at the notes for Math 1320. And you can find the Dice Coins card handout on the Math 1320 page of my website. Alright, more notation. In set builder notation, we don't list each element of the set. For example, if we're looking at the set containing 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10, we could write it instead as the set, squiggly brackets, of all n, such that, that's this little line right here, such that 1 is less than or equal to n is less than or equal to 10. Now something like 1 through 10, we could list them. But if I asked you to write down a set of the first 1,000 counting numbers, you wouldn't want to sit down and write every number between 1 and 1,000. And inequality, set builder notation might be a better way of doing that. Sometimes visual representations of sets will make them easier to deal with. In that case, we'll use Venn diagrams. Venn diagrams consist of a rectangle, our universal set, with sets generally represented by circles. That's how we'll do it in this chapter, in these sections. Alright, so let's look at some Venn diagrams for these interpretations. The intersection of sets A and B is written as A and then this little upside down horseshoe, and it represents the set of all elements. We're going to pretend that's a rectangle. Set of all elements that are common to A and B. So if I have a set A and a set B, my intersection is just the part in common. All right, intersection is the overlap. Intersection is the overlap. Now if I have the union, we have a rectangle. Our universal set, we have a set A, and we have a set B, and the union is all of A and all of B and all the stuff that they have together, all right, inside of the intersection. And finally, if S is the universal set and A is a subset of S, then A prime, A complement, this little symbol here. Boy, that's ugly. There we go. A complement, the little apostrophe looking thing, is the complement of A and S. So if I have my universal set, here's my set A. Let's call S the universal set. A complement is everything in S that is not also in A. So I'm going to write it here, A complement. So 3 different things that can happen. If we have 2 sets, A and B, we have the intersection. That's their overlap. Think of this as the first date. On the first date, you only talk about things you have in common. The union, that's more like marriage, right? It's all of your stuff, all of their stuff, and all the stuff that you got while you were together. It's a union. It's all of A, all of B, and what they share. The complement is the opposite. So in my sample space S, if I have a set A complement is everything outside of A. Alright, Venn diagrams. So let's list some elements of each set. Number 1, the set F consisting of the 4 seasons. F will be the set, so squiggly brackets, spring, summer, fall, and winter. The order that you put your seasons does not matter. The language that you use does not matter. There's 4 seasons. Put them in there, you're good to go. Set of outcomes of tossing 2 distinguishable coins. If the coins are distinguishable, let's make them specific here. We'll have a quarter in gray and a penny in a copper color here. Then the outcomes are quarter heads, penny heads, quarter heads, penny tails, quarter tails, penny heads, and quarter tails, penny tails. All right, 4 different options if the coins are distinguishable. List the elements of the set of all outcomes of tossing 2 indistinguishable dice, such that the sum of the numbers is 8. So they're indistinguishable, so maybe they're both white. We're playing a game of Monopoly. So we don't know if the first one was a 6 and the second one was a 2, or the first one was a 2 and the second one was a 6. It doesn't matter. That's the same rule. One die shows a 2, the other one shows a 6. If they're indistinguishable, we just list it one time. A 2 and a 6, a 3 and a 5, a 4 and a 4. Those are the only 3 ways that we can roll indistinguishable dice so that the sum of the numbers is 8. Whereas if the dice are distinguishable, now the sum of the numbers is 8. If we have one die in blue and the other in red, now the order that they're rolled matters. The blue die could show a 2 and the red a 6, or the blue a 6 and the red a 2. The blue a 3, the red a 5, or the blue a 5, a red a 3. Or they're both 4s. Notice there's only one way to roll the double 4. They're each a 4. Whereas the numbers that are different, 5 and 3, 3 and 5, 2 and 6, 6 and 2, there's 2 different options based on which color has which number. Alright. Let A be the set June, Janet, Jill, Justin, Jeff, and Jello. B is the set Janet, Jello, Justin, and Bob. And C is the set Sally, Solly, Molly, Jolly, and Jello. We're going to use these 3 sets for several examples. Here we go. If we want to find A union B, I'm going to write down everything in A. June, Janet, Jill, Justin, Jeff, and Jello. Then I'm going to write down everything in B. Janet, Jello, Justin, Bob. But now I look and I see, oh, Janet is written there twice. I only need to write it once. Jello written twice. I only need it once, so I cross it out once. Justin written twice. So it's all of A. And then only what I was missing, because I've already included the overlap, so I just put in Bob. Same sets, A, B, and C. Where does B intersect C? What does B have in common with C? Well, B has Janet, C does not. B has Jello, C does, so we have Jello. B has Justin, C does not. B has Bob, C does not. Jello is the only thing they have in common. In common, it's in in set B and in set C. Notice this little intersection we have here. The intersection symbol easily looks like an A, and the word and frequently used for an intersection. Just a little study tip. A union, B union C. So with parentheses, we do that first. B union C. So I'm going to write down everything in B, Janet, Jello, Justin, Bob, along with everything in C, Sally, Solly, Molly, Jolly, and Jello. Notice I do have Jello listed here twice. I just put everything in B, everything in C. This is a repeat, so I probably wouldn't pay attention to it the second time around. And I want to union that answer with A. So now A has June, already have Janet, has Jill, already have Justin, has Jeff, already have Jello, and then the rest, everything in B and C. So everything in A that was missing from B or C ends up in our set. A union B union C, all the names, and we only list them once, and not the 2 times that I have Jello listed. Alright. Number 4. What if we do A union B first, and then union C? Well, A union B, that's June, Janet, Jill, Justin, Jeff, Jello, and remember Bob was the only extra. Union that with C, now we put in the Sally, Solly, Molly, Jolly, and we already have Jello. Notice that's the same as example 3, where we did A union, and then the parentheses were around B union C. When we're unioning 3 different sets, the order doesn't matter. We're just using all 3 sets. Now, B union C complement. To find the complement, first let's find B union C. So everything in B, Janet, Jello, Justin, Bob. Throw in everything in C that's not already written, Sally, Solly, Molly, and Jolly, because I already have Jello. Now we find everything in these 3 sets, A, B, and C, that is not in this list above. June is not in this list. Janet is. Jill is not in this list. Justin is. Jeff is not in this list. But everything in B is in this list. Everything is C in this list. So only the 3 things in A that are not also in B and C are in B union C complement. Ooh, that's a mouthful. Cartesian products. These are named after René Descartes. René Descartes was the one that did a lot of work towards the graphing of algebraic geometry so that we could see what's going on. And these Cartesian products come directly from what we know with plotting points A and B. So the Cartesian product of two sets A and B, right? Sets A and B are capitalized. Is the set of all ordered pairs, little a comma b, little b, with A an element of the set A and B an element of the set B. So A cross B is just elements of A and the elements of B. For example, if A is the set small, medium, and large, B is the set of UTEP school colors, blue and orange, and C are the shapes triangle and square, we can list the elements of a couple of different sets. Still have small, medium, large, blue, orange, triangle, square. The elements of A cross C, order matters. A comes first, small square, small triangle, medium triangle, large triangle, small square, medium square, large square. Wow, I didn't do that very well, but small triangle, medium triangle, large triangle. Elements of A come first, has to be small, medium, large in the first coordinate. Elements of C come second, so I used the triangle image rather than the word, and squares. The elements of C cross B, C is triangle and square, B is color. So triangle blue, triangle orange. Square blue, square orange. It doesn't matter, you could even do triangle blue, square blue. Triangle orange, square orange. The order doesn't matter as long as you have the triangle or square first and the color second and they're each in ordered pairs. That's all you need for a cross product. Alright, so that's sets and set operations. We have union, intersection, the complement. We have cross products. And next we're going to learn how to count the elements in these sets. That's it for this section. Thanks for listening.